one of you raised a few issues about the lab assignment. So I suppose we need to, but then he found a mistake. I think he found a mistake, but then we need to check. We need to have a look into it for a little bit and emphasize the strength of the model order reduction subject we do study here, okay?
Okay.
So there was this discussion about the controllability and the observability of the CD player model, 120 size. Well, in some sense, it's a small size. I mean, essentially, this is something that MATLAB can usually handle. However, even in this case, depending on the size of the numbers present in the ABC matrices, the results can be quite surprising or quite unpleasantly surprising. Okay. So loading the CD player, if you have a look at the A matrix, trying to open the A matrix. Okay. So we've got a lot of we've got huge numbers if you see here. Yeah. Okay. So this is 10 to the power 4. So these are large numbers. These are large numbers. They're not very pleasant. Okay. So when we do compute something about this can be quite difficult. And I was asking you to check the controllability and the observability of the CD player. First, of course, the thing you can do is attempt to build the controllability matrix. Okay. So CD, first of all, you need to make up a state space system. So we use SS, A, B, C, and I think it's zeros 2 by 2. Yeah, because we've got 2 inputs and 2 outputs. Okay. What's wrong? The image is moving from sparse to full. Oh, okay, fine. Okay, so this is a full matrix. Okay. The A matrix. Okay, so this is our system. Okay, fine. So now R is CTRB of the CD. We don't have to look at it. We just compute it. Then we check the rank of the matrix R. Essentially, it should be 120. This is a minimal realization whatsoever. Well, as you can see, it's not working. Okay, so this is not a good way. This is not a good way to perform the controllability testing. Okay. On the other hand, if you do try to have a look at the eigenvalues of A, okay. Why are there so no? There are not so many. Anyway, it's not working properly, this one either, but I think first of all we should do this. I think this is the command, right?
Yeah.
And now let's try this again. Oh yeah, there you go. So you've got, this is not a symmetry matrix, nothing. So essentially, and you can see again, huge numbers, 10 to the power 4. This is not something we enjoy, okay? But this, the A is stable. At least the matrix A is stable. This is what we can see here, okay? Because they are usually ordered, and you can check And as you can see, all the real parts are negative. Hence, the matrix and the system are stable. Okay, fine. However, the CTRB let's see, maybe if we do this, things are going to be all right. Let's see, is 4. See. Fine. So CTRB. Oh, we have to make the system again. So CD is SS A B. Actually, we can just run it once again. Okay, now we make the system with the full matrices. Should work now. Oh, you see it worked now. Let's see if this works, then it's all right. You see, it's still not working because of the numbers. They are ill-conditioned numbers. Okay, these are ill-conditioned numbers. Okay, fine. So we have to do something else. Okay. Let's see if this works. I'm trying a little trick. I'm not sure if this is working. Now I'm taking the Hankel matrix, QR. Why is it not possible? QR. Oh, you see how bad they are conditioning. So they can compute. He can compute the observability matrix are not of cis. Sorry, wrong. I mean, it's not cis but CD. Sorry about that. Okay. Same issue. And probably it's not going to be possible to compute the rank of the Hankel matrix, as you can see. Okay, so nothing is working if you can easily see. Okay. However, we can try to compute the gradients. The gradients are the savior. They're going to save us. Okay. So we take the W to be this guy. First of all, let's try the simple LIAP. Have the simple LIAP. And let's check the rank. Not working. 116. The rank should be 120 if this is minimal. So that means it's full of ill-conditioned zeros in this when solving using the simple LIAP. Okay, the simple LIAP. So we are going to use LIAP call. Okay, let's see what LIAP call does. LIAP call scheme. So this is a Lyapunov, a method to solve the Lyapunov equation using the Kolesky factors. Okay. Use the Kolesky. You see. First of all, this command works. You can see here if the matrix A is stable, which is stable for the CD player. Okay. It's a square root solver, of course, because this is R transpose R, as you can see here. Okay. All right. So essentially, the LIAP call is computing the Kolesky factor. The Kolesky factor of W. Actually, this should be W1 or WL. Okay. WL. Because
Teacher?
your W, yes.
It should be B there, not B transposed.
Why not?
Because as you
Oh,
can see,
AB. Oh, okay.
it's
Okay.
a bit different from the
Yeah, it's different than the app. Sorry about that. Oh, shoot. You're right. Like this, okay? So WL times W. So the controllability gradient W is WL times, or WL transposed WL, right? Now let's see if this works. If this doesn't work, at least we can check the rank of the factor. Oh, this doesn't work either. This is 120, you see? So it should be all right. It should be all right because this is controllable. Okay. At least the Koleski factor can give us a precious answer. Same applies to the other one. Not this one, but this one. QL AC transposed, right?
and A transposed.
And A transpose as well. True. That's right. So rank QL is good. And then we have QL transpose, right? Or the other way around. It's the same anyway. Okay, but at least the Koleski factor indicates that things are doing all right. Okay, because you cannot apply the factorization. You have to have the rank condition. Otherwise, this is not possible. So things are pretty much all right, but they're difficult to assess. That's the issue. They're very difficult to assess because of this dimension 120. Okay, and again 120 is very, very small. It's very, very small. Okay, imagine if you had 1,000 or 10,000 or so. Okay, again, it's not only the dimension that's the issue. The issues are also the numbers inside the matrices. Okay, the numbers inside the matrices are also quite important. Okay, because otherwise the results are not what we expect them to be. Okay, they are not what we expect them to be. Okay, so this was the discussion on lab 3, I guess. All right. So I suppose that for the building it's much easier, huh? Or not?
Yeah.
I suppose it works because the building is 50 or 48 or something like that. Should be possible. Okay. You should encounter, probably, I'm sure you didn't get any problem. There is no problem there, I suppose.
Yeah.
Yeah. So this is the issue. This is the power. That's why this lab emphasizes the motivation for this class. Okay. We learn about these methods as you saw the balance truncation last time. We emphasize methods to approximate these large-scale systems with smaller systems, meaning the same thing. Okay, what this meaning means, okay, this is something we discover. So for balance truncation, the meaning was the importance of the dynamics from an energy point of view. Okay, reducing the H infinity error norm. Okay, that's what balance truncation does, and balance truncation is a beautiful theory, very clear, okay, with powerful results on error bounds and stability preservation and all these things. However, the balance truncation is suffering from this critical issue of the of the solving the Lyapunov equations. Okay. What's wrong here? Oh, sorry about that. So let's try again. WL is this. L is this. And now I'm trying to make the product, okay? Because we know that the Hankel singular values are the eigenvalues of the product WQ. We know that. So we try to look at the Hankel singular values and their distribution. So what name should I give? M or sigma or S from sigma is WL transposed times WL times QL transpose times QL. Okay, I'm using all the factors. So I have this matrix S. Now I'm computing egg S. You see? So we have a big issue. Essentially, so this is 10 to the power 12, if you can see here, okay? So again, these are quite interesting numbers. However, if you go back here, you're going to see a lot of things close to zero, okay? How do you do this? You usually, because I want to see not full, what's the command if you want to see the numbers with all their figures? Do you know?
With what?
So I want to see, I don't want to see it in this form. I want to see it in long format, long form. Help long long form. No, what's the name for this? Huh?
I don't understand what you
So
want.
I want to see the whole numbers. I do not want to see it in this form with the power here. I want to see the number.
Okay.
There is a command, long format, long form, short form, long G, long something. No. Oh, damn. Let me look it up. I'm looking up.
It says that you can use the command format long
Format long. Okay, format long.
to change the printing settings, but
How do you do that? How do you use it? Format long in one word,
no, space.
like this.
Yeah, but not without help. Just use that command.
Format long like this.
Yeah,
Okay, thank you.
and print again.
Okay. There you go. This one. You see? Oh no, it's the same one. Why do I see this once again? I don't want to see this. Format long.
Another way is to use sprintf, and you.
Okay. S.
I post in
This.
chat an example.
Okay, put it on the chat. Okay. Okay, chat. So S print F. And what else did you write there? What is
I don't know
this?
why it's colored.
No. So I'm asking you S print F. You had percentage 16 dot F, and then
Yeah, you say you hard code it as to show a number of decimals
of
before
digits.
or after of digits before or after.
Aha.
So in our case,
I'm going to do this. What you showed me like this.
yeah. But instead of that long number, you put that variable s
Here.
or
So I
not
want
s.
I of S.
Yeah, that one.
Like this. It's not working because I don't see everything. I only see a part of them.
Ans. Maybe in workspace at the ends field.
No, at the
There are
answer.
more.
Okay, here, this one. Okay, I have it here.
Maybe there are more.
I'm opening it, but it's only one of them.
Ah.
No, I should put it again. Oh, there we go. But it's again, it shows me with the E stuff. Complex double. Damn it. No. I want to see all the numbers. You understand what I want to show you.
Yeah.
Oh, but it's actually showing all of them. Oh, so you see? Look, from this one here, they're all zeros. You see? So they are very, very small. They're very, very small. They count only until this moment. So what dimension should this one be? 1, 2, 3, 4, 5, 6, 7, 8. Shoot. No, sorry, let me try again. So again, I'll go from down up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 30, 31, 32, 30. So about 35 dimension. Then from 35 onwards, nothing counts, you see? They are almost not controllable and not observable. So this is rubbish. You understand what I'm saying? Okay? So that's why you get these bad results. Look at the Hankel singular values. This is the distribution. This is their distribution, okay? Okay? Let's see Bal Real. You'll have to play with these yourselves. So you need to make a full analysis of this later on, probably lab 5 or 6 or so. Yeah? Look. So Bal Real computes a balanced state space realization for the sys, for the system. What's G? Look, G is for the Hankel singular values. Let's do this for the CD player. So CD Bal, so balanced CD player model. G is Bal Real, not 0. Is Bal Real CD. There you go. Oh dear. You see? These are the Hankel singular values. Just like I told you. These starting from a certain number, they are very, very small. Okay. Ball real is more efficient than multiplying W and M. Okay. Ball real is more efficient. Okay. All right. So you see, the last two actually are really do not count. They really do not count. But actually, you can see here, from a certain point, none of them count any longer. Okay. All right. You can see. You see this decrease. You see. Look at the first two. They are the most important. Okay. And then the other two, they are because you have to go to the 6 digits. Okay. Let's try again our friend's command sprintf. Maybe this is working. I'm going to put here G, okay? Well, anyway. Still not working, but anyway.
Maybe a sprintf is only for a number, not for for an array.
Not for an array. Okay,
Yeah.
never mind.
Maybe it needs a for loop.
For loop. Okay, never mind. Let's go again with the format. No, this is the longest format possible. Okay, yeah. So you can see here, the Hankel singular values tell you everything. Okay, it's minimal, but it's almost non-minimal with these two. Okay, with these two. All right. So that's why you had a lot of problems, because you have these very small Hankel singular values here. You see. So this is almost close to NaN or inf, those results that you see for MATLAB. Okay. This is the reason. The reason is the very small Hankel singular values. Okay. So that's why balanced truncation is called for. That's why we do mod-red and the other things you are going to do, okay, with a specific error given by the eigenvalues that you throw away, okay, by the eigenvalues that you throw away. This is for you to do approximation of the CD player, good approximations of the CD player, okay. I just showed you the issues you have with the CD player as it is. If you have any questions here. Hmm?
I have a question.
Yes.
What is the difference between W and WL?
W and W, which one?
Yeah,
L?
yeah,
Sure.
yeah.
This is the
Those two.
Cholesky factor of W.
Okay.
So W
Okay.
is WL transpose W, L.
Okay.
Okay. So if you look again, if you go back to help Liap call, R, you see? So this command is not computing the Gramian, but the Cholesky factor of the Gramian. So it's computing this guy. You see?
Oh, I see.
So
Okay.
once you compute this guy, you need to do this multiplication to recover your full matrix. You need to perform this, okay? But again, it's a good command, this liap call. Yeah. Anything else? Anything else?
No, at the moment.
Okay, fine. Do your assignments. That's all I can say. Okay. Okay, so last time we discussed in detail the model reduction of you based on balance truncation, and we went through all the chapter in the Antulas book, okay, emphasizing some of the issues worth investigating when you do balance truncation of different types of models, because as you can see, there are many things to be taken into account, okay? So, and you can adapt your balance truncation method to the peculiar class of systems you are trying to approximate, okay? So whatever suits you, that's the good method you can use, okay? You always have to find a suitable method, okay? So to draw some conclusion over the past, over the whole discussion about this very nice or very popular model order reduction method. So essentially so everything starts from the so-called balanced realization of a dynamical system where the states which are difficult to control and have no powerful influence on the output are emphasized through the invariant quantities called Hankel singular values. Okay, so to each state there corresponds a Hankel singular value. Okay, if the Hankel singular value is small, then it's hard to control in the past. And if you turn off the input, the influence at the output is insignificant, and vice versa. If the Hankel singular value associated with the state is high, then it's very easy to control and has a lot of influence on the output. So this is worth keeping in your approximation. The rest can be neglected. They can either be truncated, so you set them to 0 and you keep a portion of the system which is relevant to you, or you can do singular perturbation in the sense that you set only the dynamics to 0 and then you have some algebraic system, you compute the solution and you use it back in your model. Okay. So difficult or easy to reach and difficult to or easy to observe. Okay. In this case, the minimal energy required to reach a given state is the inverse of the observation energy generated by the same state. Okay. Yeah, because LC associated to an xi is 1 over Hankel singular value index I times xi squared, and the same energy is Hankel singular value, the same output energy is Hankel singular value squared times xi squared. Okay. It says here that mathematically balancing amounts to the simultaneous diagonalization of two positive semi-definite Gramians. Yes, that's what you have to do. So from a theoretical point of view, there is no big deal. Okay, so you just do diagonalization. Why you do diagonalization? Because in general, the Hankel singular values are distinct. They are not equal. However, there are applications where they can be very close to one another, and then that's an issue. That can be an issue and that can cause problems, and there are many adaptations, okay, many amendments brought to the balance truncation to cope with this situation. However, in general, most of the dynamical systems exhibit a specific decay of the Hankel singular values. And you noticed in the CD player, the first two were very large, the next two were rather small, the other next two were even 10 times smaller, and so on and so forth. So this is a very strong decay. Okay, usually what people do, they perform what is called a Hankel singular value plot. Okay, So here you plot the Hankel singular values versus time or something, and you show the decay. This is the first one, this is the second one, this is the third one, the fourth one, okay? And then the fifth one is very, very low, and then the decrease is not so powerful. So this is a typical graph. This is a typical graph of the distribution of the Hankel singular values of a linear system. However, this is not always the case. Like I said, at a certain point, this can be very, very slow. Okay. If it's very, very slow, you cannot essentially know where to cut. If here you know you have to cut here, because you can neglect all of this from here to here. In this case, you don't know where to cut, here or here or here. You just have to do some sort of trial and error. Okay. Again, the theory is very solid when this situation occurs, when you have a specific decay. When the decay does not occur, then the theory has to be amended. Okay. Okay. Yes, indeed, it's one of the most effective approximation methods. Approximation through balanced truncation. Properties: stability is preserved, and this is huge. And then you can have the second huge quality is that you can get a computable error bound a priori, so a theoretical error bound. And this is something outstanding. You don't have this in general. In numerical algorithms, this is seldomly possible. Maybe optimization can do that. Okay, if you remember from optimization techniques, if you remember Professor Nequara's all sorts of presentations, he was always showing you convergence rates and bounds and errors and so on and so forth due to, especially in the convex optimization case, okay? Mind you, the balanced truncation in an optimization sense, because you minimize the control input energy, so there is minimization involved, is not a convex problem. Because you try to minimize essentially or go to or think about minimizing the H infinity error norm, and that's not at all a convex optimization problem. That's why this result is extremely powerful. Okay, because for this apparently strange problem, you can actually find, so essentially there is a relaxation somewhere, because you can actually find an a priori error bound, and this is awesome. This is huge. Okay. Okay. The latter provides a trade-off between accuracy of the approximation and the complexity of the approximant. Okay. Just as the singular values of a constant matrix provide a trade-off between accuracy and complexity of row-rank approximants. This is a powerful and very nice statement Mr. Antoulas is doing here. Okay. This is a very good comparison. So think of numerical methods, okay, matrices, constant matrices, okay. You always get a trade-off between low-rank approximations, okay, and accuracy and the singular values. That's why we compute singular values. We don't compute singular values for the fun of it, because some guy was smart enough to cook up something just to make life funnier. No. Far from it. Okay. The idea is that the singular values of a matrix are a critical measure, a crucial measure for the importance of the elements in a matrix. If eigenvalues represent the core definition of the matrix itself, they are like the birth certificate. Let's put it this way: eigenvalues of a matrix are a birth certificate. Why? Because you can always give birth. Okay, this is ridiculous, but it's fun. You can always give birth to a matrix through a set of eigenvalues. You can always pick a set of numbers, say these are eigenvalues, and then you compute the characteristic polynomial, and then you generate an infinity of companion matrices. Okay, so it's like a birth certificate, whereas the singular values of a matrix are the identity card of the matrix. Okay, it's like the health card. Okay, so the singular values express a measure, a norm. Okay, eigenvalues can also bring a norm, but this is not so important. But the maximum, for instance, the maximum and the minimal singular value of a matrix do have a specific meaning. Again, they are like the identity chip-based 5G card. Okay, so you can be happy. I'm teaching you Bill Gates here. Okay, but the comparison is very good. So I like what Antulas is doing here. I'm stressing this again. I'm not merely doing propaganda here. I'm not selling this book to you because it's far from my interest. I honestly don't give a shit about this because Antulas is Antulas. His book is his book. Since or it's gonna be now 16 years now. So there is no interest in that. But I'm telling you, if one of you is interested in understanding the world of linear dynamical systems and their approximations, this is like a Bible book. It's very nicely. It has all sorts of comparison, especially something which I'm not very familiar with and something which I'm not very fond of, because I like more fundamental stuff and analytical stuff like theory. But he's doing it from a numerical point of view, which is very popular nowadays. Like I said, I don't give a shit about numerics if you ask me. It's rubbish in my mind. But okay, I have to teach you normal things, so I have to care about these things. Okay, and I also do research in this field, so I also need to care in research about these things. I can't just leave them out of my life. I can't just put them aside and move on and say, okay, I have a nice theory. But if I can't compute anything, my theory is essentially worthless, isn't it? Hence, do read this book if you people want to do linear dynamical systems. Okay, this is not a control book. There is huge, nice control books. This is not control. This is modeling and model approximation, which is essential if you ask me. Because I'm telling this now at the middle of the class. Okay, we're in the middle of things, but please do understand that if I do not have a good model, control is essentially useless. Okay, so the control is not worth a crap if the model is not good, or the model is useless. Like this, you see the CD player. Okay, if the numbers, the crunched numbers inside this model, okay, stemming from identification, stemming from all sorts of modeling issues, if the numbers are ill-conditioned, control is rubbish. Because, mind you, this is not a pendulum or a simple system with 2 states and 3 states where you can do analogical control. Okay? Keep it in mind. Analogic control is easy. Analogic control is very safe, is very accurate. But digital control, because essentially now you build controllers, you do control on computers and so on and so forth. Even for our friend in economics, people do use computers, okay? They don't compute stuff using pen and paper. When they compute risk management and all these things, okay? There is also control in economics and macroeconomics. They don't do this on paper. They need to do it on a computer. So you do need well-conditioned and nice numerical algorithms. The same holds for control. So before doing control, in my opinion, but of course, from a teaching perspective, this is not possible. But logically, or at least at this stage, the first step is you need to understand this book, and then you need to go study control engineering and all sorts of things. Okay. So essentially, what I was doing here was a lecture about. I'm lecturing about how you should approach the world of control from a research perspective. Okay, philosophically speaking. Of course, you can do anything, but I'm just saying how it should be done. Okay, and then it's telling you how you can get the main results. So balanced truncation, very important. I advise you to read again in this book and other books, and also please do search online. There's numerous, there is a vast number and several lectures and online lectures and YouTube lectures about balanced truncation. So if you're interested in the subject, Please do read this again. I have a PhD thesis in balanced truncation for nonlinear systems. A part of it, my former PhD supervisor, she was the one who invented balanced truncation for nonlinear systems, like the pendulum, for instance. Okay, where you have the signs and all these things. But then of course, I was suffering from the same issue that balanced truncation is suffering from. That's why recently it has been left aside due to the computational issues. The questions you raised in your lab 3 there, these are questions that linger on in the balanced truncation problem. The solution is bound by this and is biased by these Lyapunov equations needed to solve the Gramians. The Gramians are the first step before you do a balanced realization, because if the Gramians didn't exist, balanced truncation would be hugely popular and we would not be discussing model order reduction today. But because the Gramians are solutions of Lyapunov equations, things are getting difficult. There is this guy who used to be in Chemnitz and now is teaching at the Max Planck Institute in Germany called Peter Benner. You can look, the guy who has the website modelreduction.com, which I invite you to consult for further reading. Peter Benner has been struggling for years to convince people that balanced truncation numerically is wonderful because you can do low-rank approximations of Lyapunov equations. After 10 or 15 years of doing that, the guy quit because the other methods were much faster than balanced truncation and had more reliable algorithms, as we'll see when we'll discuss about Krylov-based methods. Okay, where efficiency is the first and foremost, or in the foreground, if you ask me. Efficiency, it's all about efficiency, leaving aside the theoretical aspects. You'll be surprised to know that the efficient, but this is from Murphy's laws. This is something you get in life. It's a trade-off. So balanced truncation is a wonderful theoretical method with error bounds and stability preservation and this and that and wonderful theory, but hard to compute. Just like if you look, just like Hankel singular values discussion. Whereas Krylov-based methods are extremely efficient from a numerical point of view, but are rubbish from a theoretical guarantees, not theoretical point of view, because they also have nice. And I'm going to present you the most recent perspective on Krylov methods. I'm not going to present it to you like in the book of Antulas. You are going to read about Krylov methods in the book of Antulas from the numerical and algebraic perspective. I'm not going to do that. I'm going to introduce you, not today, but in the next lecture, Krylov methods from a systemic point of view. And you'll be surprised how simple the method essentially is, and the significance is very clear. But from a theoretical perspective, you cannot preserve stability. You do not have an error bound. Essentially, you get nothing from this point of view, okay, from this angle. But it's very interesting, okay? Fine. Let's move on and go now. So balanced truncation has byproducts, okay? If you remember, the error norm was computed. Okay, so we had the infinity norm because we were computing the ratio between the output energy, the future output energy, and the past input energy introduced in the system to control it. And doing this ratio, you know from second year that when you have the ratio between two energies, you get the infinity norm. Okay, so essentially, I remind this is something you learned in the second year. I'm talking about people in control here. You learned in the second year, okay? So that if you had this perspective, so you have here a system, okay, let's call it G or S, whatever, a transfer function, and you get an input U and you get an output Y. I remind you that these are convolution systems. So in the time domain, this is G convolution U, because essentially the output of a system is the echo of the input through the system. That's what convolution means. Convolution is the operation of echoing. Okay, you build an echo. Okay, so essentially this is something you know from the second year, that the energy of the output is bound by the energy of the input multiplied with the amplitude of the system. So that's why this is related to the Hankel singular values, and then you get the error bound from the balanced truncation due to this relation, essentially. Okay, this is the basis for the theory we saw last time. Okay, but you can also look at something else, and this is something we are going to have a look at soon. So we do keep in mind this relation because we are going to use it. Okay, but then there is the other issue, looking at the amplitude of things. So what about the maximal amplitude of the output? Is it bound? Of course, it's bound by the maximal amplitude of the input multiplied by the 2 norm of the system. Okay, so the question, this raises the question, what is, in model order reduction, the 2 norm of the error system? This is another measure of the accuracy of model reduction. Okay, so keeping this in mind, we are going to look in a couple of books. I've got no slides for this because I don't need slides for this. So we're going to look in a couple of books about minimizing the approximation error norm. Mind you, balanced truncation is not minimizing any error whatsoever. It's just computing an error bound. That's not bound by there is some optimization in the background, but it's not the optimization of the error as a cost function. Okay. So now we have to ask ourselves, can we use the error norm of the model reduction as a cost function to formulate an optimization problem? And the answer, of course, is positive. Of course, you can do that. Okay. So we are going to look at these methods involving minimizing an approximation error norm. Okay. Minimizing an approximation error norm. Okay. And of course, we look at the H2 norm. So this comes from the relation, and again, okay, so this is error, this is the error signal, okay, y minus y approximated, okay, infinity norm. This is bound by the error system 2 norm times the maximal amplitude of the input based on this relation, okay? Based on this relation. So can we get something out of minimizing such an error norm? So again, the H2 norm, let alone the fact that this relation also yields an important class of control methods, okay? So the H2 norm is widely used in control systems, they say here. We consider an asymptotically stable system, okay? And we consider that there exists a reduced order model GR of G, okay? And of course, we consider dr equal to d, so things are easier, okay? There is no loss of generality in making this assumption, okay? What is the realization of the error system? That's the first question. So the error system itself is another dynamical system of the same type, okay, so from the same class with G and GR, and is given by a specific realization. So what is an error system? If you have two systems, G1 and G2, okay, so this is output Y1, this is output y2, and usually they are connected to the same, they are excited by the same input. Essentially, to build the error between the two outputs, okay, you get an error signal, which is y1 minus y2. But this is a parallel interconnection. You recognize it? This is parallel interconnection. Parallel interconnection, okay? So if you do G1S minus, so essentially, no, you had this, okay? You had y1 minus y2. You take the Laplace of this, and then you get y1s minus y2s, okay? This is C1 Si minus A1 inverse B1 minus C2 Si minus A2 inverse B2. Okay. All right. So this can be shown. We don't. We won't stop over this here. This can be written as C1 C2 times Si minus A1 Si minus A2 not squared. Okay. And now you can put the inverse here. Okay. B1, B2. This is easy to see. Okay. Why? Because this is a block diagonal matrix. So this is Si minus A1 inverse, Si minus A2 inverse. Okay. This is block diagonal. Block diagonal, okay? And you know that when you invert a block diagonal, a diagonal matrix, essentially you just invert the diagonal elements, okay? I hope you remember, if you have M1, M2, 0, 0 inverse, this is 1 over M1, 1 over M2, okay? So this is essentially, so the realization of the error system is given by this realization, okay? The matrix A is the diagonal, block diagonal matrix with A and AR. The B matrix is just the augmented matrix B, BR, C, and here you have to have minus, of course. I forgot about it. Indeed, at a certain point you have to have minus here. Okay, so you can easily get the minus sign, okay? Furthermore, the H2 or the L2 norm of the error system is given always by this relation. This is a very well-known relation from dynamical systems. We do not stop now to understand this relation. If you can look it up in the books or everything or anything. But the 2 norm of a dynamical system is essentially given by the controllability and the observability gradients of the system in this form. So the 2 norm is the trace of CP C transpose or the trace of B transpose QB. So the 2 norm of a dynamical system, first of all, the 2 norm exists only for stable or unstable systems. The 2 norm does not exist for systems with eigenvalues on the imaginary axis. But we know that here this is asymptotically stable, okay? This is asymptotically stable, so that means that the spectrum of the matrix A is in C minus. That's what stability means, okay? So you can have this relation. The 2 norm of the error system is given by the trace of these quantities involving the controllability and the observability gradients, which you can see here because they're the solutions of Lyapunov equations. So what is the problem essentially? The problem here you formulate. What's the problem to formulate? Yeah, the problem is solve mean by all GR functions of G minus GR2 norm. This is the problem. Okay. All right. When you know you have A, B, B, C, D, this is known, and you need to minimize by AR, BR, CR. Okay, D doesn't count at this point. Okay, so the minimization is done over these matrices. Yeah, this is the problem formulation. You can realize, you can easily see that, first of all, the two norm being a norm, it's always positive. Keep this in mind. So this is a positive number. Okay. So this is a non-convex problem, as you can see here. Yeah, it's a non-convex infinite dimensional optimization problem. Okay, and there is no unique global minimum. Okay, because the coordinate basis they say here can be adjusted can be adjusted without changing the error. So there is no unique global minimum. Okay, numerical algorithms solving the optimization problem can get stuck at local minima. Okay, which are not global minima. And you have here some references vouching for that, okay, confirming this. Okay, so how do you avoid the non-convexity of such a problem? Okay, it says here that one way to avoid the non-convexity is to assign the poles of the reduced order model before minimizing, and to regard the unknown parameters as entries for CR and DR. So essentially, to avoid this issue, you change the minimization from the matrix AR to the matrices CR and DR. If you ask me, this is not the best way to do things. I always, in my research, because I'm also researching this kind of methods from the time domain moment matching perspective, we also try to minimize the location, or to get the locations of the poles of the reduced order model of AR matrix as a solution of the optimization problem. We do not fix that from the very beginning. I don't think this is the way to do it, if you ask me. The pre-assignment makes the problem simple so that solving one linear equation is enough to obtain the unique solution. Okay? They say, of course, you see here, the achieved error may be considerably greater than the achievable in principle when poles can be varied. Exactly what I told you a minute ago. So fixing the poles from the very beginning is not the way to go if you want a more accurate model. However, for practical reasons, their assumption is lucrative, if you ask me. Okay. Okay, so earlier we described model approximation through balanced truncation and considered the equation of the resulting frequency error domain. Okay, it's natural to ask about the L2 error when balanced truncation is used. Okay, what can be said? So balanced truncation yields a result about the infinity norm. The question is, what does the balanced truncation say about the two norm of the system? Is there any connection to that? Apparently, there is, or I wouldn't say obviously, but apparently there is a connection. There is a connection. Okay. Okay. There is no simple relationship, okay, between balanced truncation and the two norm. And essentially, look, you see the balanced truncation achieves a good infinity norm, but a bad L2 norm. Okay, but that's again a trade-off. You cannot have both norms very good. However, you'll see in the moment matching case from a practice point of view, in practice, you'll see that in moment matching you can achieve both low infinity and low two norm. Okay, and here they give an argument. You suppose ABC is in balanced form with these Hankel singular values, and you have this decay present. Okay, and then you denote the ith row of B and the ith column of C to be BI and CI. So there exists VI, BIB transpose CI transpose CI equal to this value, minus sigma I, which is the ith Hankel singular values, over 2II. Okay, so you can compute, based on that, you can compute the H2 norm of the error for balanced truncation in these forms. Sigma, so you can see the Hankel singular values also yield also yield the 2 norm of the error system. However, look at the form. The form says that if the Hankel singular values are large, the 2 norm is large, so if you need to truncate for the low Hankel singular values, but low doesn't necessarily mean a very small number. You just look at the decay, like I said earlier. I'm stressing this. You look at the decay of Hankel singular values, and which may not be the case to have a very low number. Okay. Okay. Thus, in a rough sense, the ith entry of the state vector contributes, you see, the contribution of each state vector to the L2 norm. Exactly what I told you. So it's clear one could have sigma n much smaller than sigma L and Vn much larger than Vi for I non-n, and in particular for I n. So in this case, the reduction by 1 can change the L2 norm substantially. Okay, so any truncation, even for one order, can give you a bad L2 norm. Okay. H infinity norm. So there is the discussion of minimizing the so in balanced truncation, minimizing H2 norm is not possible. That's the first conclusion. The H infinity norm has an error bound. Okay. But you cannot, there is balanced truncation is not entailing any sort of optimization for the H infinity norm whatsoever. Okay. It says here there exists no good analytical method to minimize the H infinity norm of the error system. Okay. You can of course apply a numerical method, an iterative method to solve it. Okay. But there is no good result in this. Okay, so we have to resort to another type of error norm, and this is the Hankel norm. Okay, Hankel norm approximation, which will be explained in the next session, gives a suboptimal but not far from optimal solution of this problem. Okay. It's possible to pick the initial reduced order model intelligently. That's what it says. So at least this method we are going to discuss of the Hankel norm, of minimizing the Hankel norm, can give good results. Okay. Furthermore, if the poles are prescribed from the very beginning, the poles of the reduced order model are prescribed from the very beginning, a convex problem can be obtained. Okay. It's possible to choose as the prescribed poles those arising from a Hankel norm approximation problem and then use convex optimization. Okay, so these poles do not need to be achieved to be set from the very beginning, very simple, but they can also be the result of some optimization problem. Okay. Okay. I'd like to go to this. This is important. I want to show you can read the rest of it. You can read the rest of it about these equations, okay, and the minimization involved there. But I want to go to this important class of methods called Hankel norm, or gathered under the roof of the Hankel norm approximation. Let's see what the Hankel norm is. So first we need to define the Hankel operator, and then its norm, because the norm, the Hankel norm is not just a norm as it is, but it has to be the norm of something. Okay, the norm of who? It's the norm of the Hankel operator. Okay, so who is the Hankel operator? We discussed about this a little bit before, if you remember. Okay, when we talked about the Hankel matrices. Okay, the Hankel matrix, it's an infinite dimensional matrix associated with the infinite dimensional Hankel operator. Okay, so the Hankel operator of a time invariant linear system is an operator mapping past inputs to future outputs. We discussed this before because it's related to the past input effort energy and the future output energy. Okay, formed from the impulse response of the system. Okay, so it's a time domain notion. Consider the minimal realization ABCD of a stable and proper system. suppose inputs, okay, are applied up to time t0, and we examine the outputs after. Okay, so we subject the system to inputs from a moment in the past up to 0. Then we turn off the input and let the system evolve autonomously by itself, float by itself. And there is this operator mapping the past input effort to the future output result. Okay. Okay. Then they say that the future outputs are determined by the convolution integral. This is typical. We remember this from the previous chapters. The output is integral from -infinity to 0. Okay, this is the transition matrix here, the fundamental matrix. C e to the power 8t minus tau, b u tau d tau. Okay. All right. So this equation can be considered as a mapping theta. This is not theta. This is another Greek letter. Escapes me now. Well, anyway, theta mapping signals in the L2 from -infinity to 0 to signals in the L2 from 0 to infinity. And we consider another mapping gamma, okay, mapping energy bound signals in L2 to energy bound signals in L2 in the normal flow of time from 0 to infinity. Okay, so essentially you need to set tau to minus tau in this equation 161, and then you get the gamma stuff. Okay, so the gamma is the definition of the Hankel operator. The Hankel operator is gamma applied to an input. So the Hankel operator, note that the Hankel operator, we also denote the Hankel operator by H, by calligraphic H many times. Okay, so they call it gamma here. It's applied to an input, so it's applied to an exogenous signal. Okay, so essentially you get here Y, another signal from L2. Okay, and it has this mapping. Note the plus signal. Okay, this is different from the output, from the classic output, okay, solution, because this has a plus here. Or if you want to have it in the classic form with a minus here, you need to be careful that this integral is from -infinity to 0. Okay, note that the Hankel operator has no connection to the matrix D whatsoever. Okay. Even if they say that the Hankel operator is properly, and the main definition is given by gamma, it's often convenient to look at the definition in theta, okay, because it gives the better intuition of mapping past inputs to future outputs. Okay, this is causal. Okay, past to future. This implies that there exists causality. Okay, all right. Okay, so if U is in L2 of -infinity and 0, then the output Y has this form, okay, with x0 with a system brought in x0 by the past input effort given by the input U. Okay, so we only need to understand who x0 is to understand the future output. Okay. All past inputs giving rise to the same present x0, it says here, produce the same future output. Okay. Any two literal linear case states result in linearly independent future outputs because of the observability assumption. So the system being observable, okay, you can never get two identical y's, okay, when you have different initial conditions x0, okay, because it's observable. So observability implies a difference for each. Yeah, why? Because you look at matrix Q, which has no linearly dependent columns. That's the idea. Okay. So the number of linear independent outputs n is the dimension of the minimal realization of the system. Okay. All right. So the rank of the Hankel operator is equal to the rank of the Hankel matrix associated, equal to the, we didn't discuss this, Macmillan degree of the system. I'm not going to get into the details. Minimal realization, okay, so of the system, okay. All right, I'm not going to tell you what Macmillan degree. You can look it up yourselves if you want to understand further. Okay, so what is the norm of the Hankel operator? We have to create a norm. We were discussing about some sort of norm. So the Hankel norm, we define the Hankel norm of the system G as the supremum by all signals in L2. Look, this is the supremum between gamma, between the Hankel applied, so the output of the Hankel applied to U with respect to the input effort of U, okay? Or equivalently, the supremum by all signals in L2 from minus infinity to 0 of this form, okay? So this is the output of the Hankel, okay? And this is the input effort, okay? This is the supremum, okay? So this is called the Hankel operator. The future output energy sigma U theta U squared norm says here, resulting from any past input is at most the Hankel norm squared times the energy of the input. Okay, assuming the future input is 0. So this is not related to the infinity norm. This is something else. Why? Because you look at past to future. Okay. How do you express this? So this is the definition. The relation 163 indicates or represents the definition of the Hankel norm. Now the question is, how do you characterize the Hankel norm to be able to compute something? Well, the surprise comes, and the Hankel norm is the square root of the maximal eigenvalue of the product PQ. But the Hankel singular value, so it's actually the maximum of the Hankel singular values. So this is the largest Hankel singular value, the first one, okay? The first one, because you remember Hankel singular values were sigma 1 larger than sigma 2 and so on, and then you had sigma ni much larger than sigma ni plus 1 and so on, okay? And the last one was larger than 0. So this one, sigma 1, is the Hankel norm, is the Hankel norm of the system. Who is the largest Hankel singular values, okay? By some abuse of notation, we identify the Hankel norm of a transfer function, the Hankel norm of the associated operator. Of course, this is an abuse, but this is correct, okay? Okay. And here there is an explanation about these things. Look here, you see P inverse, you can see here. You see? Look at the explanation in 166 that makes you understand why we pick the largest Hankel singular value. 166 is the key. Okay? 166 is the key. Okay. The funny thing is that the Hankel norm has a relation, for instance, with the infinity norm. The Hankel norm has a relation with the infinity norm of the system. Okay? So the Hankel norm of a transfer function matrix is bounded above by the infinity norm of the same object as seen through the following argument. But this makes sense because the definition looks like the definition of the infinity norm of a system. Okay? Remember this relation. Okay? So we go back to the relation in the beginning. Okay? Look at these relations. Isn't this identical to the Hankel norm? No, it's not identical because here there is no past and future. if you look at this. Whereas here, we talk about past and future. Talk about past and future. Okay? So look, argument. So, Hankel norm of the system G is the supremum by all inputs in L2 from the past, okay? Is the supremum over all U from the outputs in the future versus the input effort from the past, okay? But this is smaller than the supremum of all output future of all energy of all output energy with respect to the input effort. You see, so here you take minus infinity to infinity, and this is also smaller than this when you take it like this. But this one here, this is the infinity. This is the exact definition of the infinity norm. So this is the relation. Okay, the Hankel norm of a system is upper bounded by the infinity norm of the system. Okay, and the following relation holds is this guy. Oh, this relation also holds. Okay, the Hankel norm of the system is bounded by the infinity norm of any error type connection. Error type connection, where F is the transfer matrix of any anti-causal system. Okay, and of course there is arguments about this, and I'm not going to get in too many details. Okay. Okay. Now we talk about the so-called Schmidt decomposition of the Hankel operator. The Schmidt decomposition is the decomposition of the Hankel operator into its own Hankel singular values, because the Hankel singular values are the singular values of the Hankel operator. Of course, if they are so, if so, okay, then let's see the proper definition. Okay. So the Schmidt decomposition is the singular value decomposition applied to the Hankel operator, which can be written in this form. The Hankel operator can be written in this form depending on his own singular values. Okay. All right. Yeah. So where Vi and Wi are in L2, they are orthogonal. Okay, they are orthogonal, and of course also Wi, Wj are also orthogonal for I different from j, and the norm, this is normalized with the norm 2 norm of Vi being 1 and the 2 norm of Wi being 1 for all I. Okay, so the singular value sigma I of the operator are already the Hankel singular values of the system GS, of course, because the Hankel operator is associated to the input-output transfer function GS. Hence, the Hankel singular values of the system are the singular values of the Hankel operator. Okay, and you always assume that they are ordered in this fashion. Okay. All right. So VIWI is called a Schmidt pair. A Schmidt pair. Okay. Now, if we have the adjoint of the Hankel operator, okay, so there is an adjoint, okay, mapping. You see, it's applied to the adjoint is applied to the signal WT and has this form, the transposed form. It can also be written in this way. This is easy to check. You can check starting from the definition of the Hankel operator. So the adjoint of the Hankel operator is the Hankel operator itself associated to G transpose, to the symmetric of G, to the symmetric of G. Okay. So the following equations are a consequence of the orthogonality of Vi and Wi. So you have Hankel operator applied to Vi is sigma I Wi, and Hankel operator applied to Wi is sigma I Vi. Okay. we consider the L2 function Vt given in this form. So we consider V to be a command of this form and the controllability P being the controllability gradient. You note that sigma V, that gamma applied, so the Hankel operator applied to the V, to a V signal, V given in this form, is of this type, okay, is Ca to the power T x naught, okay, because this is P inverse here, and this is actually P, okay, this is actually P, all right. In the same way, you can do this for gamma star, and gamma, you can see that gamma star is this guy, where Q is the observability gradient, okay. If x naught is chosen, that this takes place with the Hankel singular values, okay, so in balanced form, sort of, then you get this form. You get this relation, this crucial relation, which can be also used as the definition of the Hankel singular values. The Hankel singular values squared of, or the singular values of the Hankel operator squared, are the eigenvalues of the operator gamma star gamma. Okay, and shows here it's shown, you can see again the relation of the energies. V squared has this relation, you see this relation here from 613 to 614. Okay, all right, so again, to sum up, GS is a transfer function or a system, has a realization, a minimal realization ABC, okay? And the Hankel singular values are sigma 1, sigma 2, and so on, sigma n 0, okay? So the spectrum of the product of the Gramians, or WM, as we call them, okay? This is sigma 1, sigma n, okay? But it is also the spectrum, or the square root, if you want, of the spectrum of this operator, okay, of this operator, all right? This is the Hankel operator, yeah? So now we clearly understand what the Hankel singular values are and their relevance and significance for what we do here, okay? Good. Now we're trying to solve the problem of optimizing this so-called Hankel norm of the system, okay? So we take it step by step, and first we present a lower bound for this problem. So to start the discussion, they say we start the discussion of approximation with a lower bound on the Hankel norm of the error in the case when the original G of order n is approximately by a stable system of order R. Okay, they use here the word degree due to the Macmillan degree. Okay. Consider GR, so the approximant, to be in RH infinity, so this means the set of all stable transfer functions with degree of R lower than n, and we consider the pair VI WI a Schmidt pair of G. Okay? All right. Okay. We consider the inputs V of this form in 1616. Okay. And then I want to say here. So since the VI, okay, they span R plus 1 dimensional space, and the Hankel operator, okay, has the rank lower than or equal to R, we can always select the alpha I, not all zero, such that gamma R V applied to gamma, so the Hankel operator of the reduced system applied to V is 0, okay? And then you get some sort of relation here, okay, of the error of the two norm of the error. Okay, please have a look at this, and I'll come back. I'll come back to you in a couple of minutes. Okay. All right. I'll see you back in a few minutes. I'm back. Are you people still here?
Yep.
Yes, you are. Fine.
Yes.
So the important result here, and I'm going to skip the discussion about it, but the important results here are these two. The first one, so the Hankel norm of the approximation error is larger than the first truncated Hankel singular value. Okay, so essentially you have sigma 1 larger than sigma 2, so on, larger than sigma r, much larger than sigma r plus 1. This is usually what we expect. And so on, larger than 0. So you usually truncate here, okay? Well, when you do truncation, or you look at this sequence of numbers, and you realize that if you truncate here, or if you use R as the reduction order, then you get this relation about the infinity, the Hankel norm of the relation 1618 for the Hankel norm of the approximation error. On the other hand, another important relation is that the infinity norm of the error, which I remind you, imbalanced truncation, so for BT, this is smaller than the sum of sigma r plus 1 up to sigma n, but this is for balanced truncation only, okay? So in general, for reduced order, okay, you get this relation. So the infinity norm is also larger than the r plus 1 Hankel singular values of the original system G, okay, of the original system G, okay? All right. We also have a suboptimal version of the Hankel norm approximation, so you do not need necessarily to get the optimal, but the suboptimal solution is also quite useful and relevant. Okay, so a first step towards showing that there exists GR achieving 1618. Okay, this relation here. Okay, we demonstrate the construction of a stable GR system of dimension R and an anti-stable all poles in the open light have plane Fs of degree no greater than n minus r, such that this relation holds G minus GR minus F for any value in the open interval between sigma r plus 1 and sigma r of G. Okay? And of course, they can also cope with multiple Hankel singular values. Okay, then GR is regarded as a suboptimal Hankel norm approximation because it never gets to the infimum. It never gets to the infimum. Okay. How do you build this Hankel norm approximation? So essentially, how do you build GR such that 1619 holds? This is the question now. Okay. You need a certain trick is used to achieve this goal. Okay, so to build Hankel norm approximations, we need a tool to embed the given system into an all-pass system. All-pass filters are those. Do you know what an all-pass filter is? An all-pass filter is that guy that satisfies the system that satisfies this condition. This is the magnitude. Okay, this is the Bode plot, the magnitude plot. So this is the magnitude of the system HS versus the frequencies omega. An all-pass filter is that guy whose magnitude is 1 for all values of omega. So an all-pass filter is H of S such that it's 1 for all omega, like this. Okay, this is what an all-pass filter is. It's used, the all-pass filters are widely used in signal processing, in digital signal processing, also in control, and as you can see, even here in the model reduction. Okay, so we use this trick called all-pass embedding. So we assume that G is a stable transfer function, okay, and has a minimal realization A, B, C, D, and we make an augmented system GA built like this, okay, and which has this system has this transfer function, okay, has this transfer function. All right, so this is matrix augmentation here, matrix augmentation, but this is just a realization, okay, where the additional 0 blocks are chosen such that we get m plus p inputs and p plus m outputs. So we make the system square. Okay, an all-pass filter usually is a square system. Okay, so there exists QA with this realization A hat, B hat, C hat, D hat, such that the error system with EA, which is GA minus QA, satisfies this condition. EA star EA is EA star is gamma squared I. Okay, is gamma squared I. So that's why you build this all-pass filter and this QA such that you get this relation depending on gamma. Okay, under the assumption that gamma is larger than the R plus 1 Hankel singular value of G and gamma is smaller, so it's between sigma R, gamma is between sigma R and sigma R plus 1. Okay, look what EA star means. EA star means EA transpose evaluated at minus S. And equation 1624 means that the transfer function EA is a scaled all-pass because it satisfies this relation. Okay. Why is this relation related? Because I told you earlier, so essentially we have EA j omega, okay, equals 1. That's what I told you. But that's what the modulus of a complex number is, if you remember. If Z is a complex number, the absolute value of Z is Z conjugated Z. You remember that, okay? But this extrapolated to transfer matrices, you get this guy. You get this guy, okay? All right? So this is where it all comes from. Okay, so this is related to this. This is related to this. Okay. We also show that QA has a stable part of degree R. Okay. And there is a whole discussion and the whole construction algorithm to be noticed here. Okay. Now, if you use P, the controllability grammar, and Q, the observability grammar of the original system G, okay, and you compute the matrix E equal QP minus gamma squared identity, you define A hat, B hat, C hat, D hat to construct QA. Has this weird construction here. And then the transfer function EA, okay, is this parallel interconnection. Okay, is this parallel interconnection because it's GA minus QA. Okay, so this is again parallel interconnection and has this form 1629. Oh shoot. Okay, it's easy to confirm. They say here that the Lyapunov-like equation holds. So this system E has again a controllability Gramian P. Okay, P index E, which surprisingly has this form depending on the original gramians P and Q. On the original gramians P and Q. Okay? But this is the controllability gramian and is non-singular, and it's also easy to verify this relation. Okay? All right? And it satisfies all sorts of relations such that this relation holds. Okay? Okay, then you have to check that there are no imaginary eigenvalues and so on and so forth. Okay. All right. These are specific details. Okay. Hold on a second. Okay. All right. So we managed to build the QA versus the GA system. We can also we also use. So we showed one particular suboptimal Hankel norm approximation can be found. Okay, in terms of QA. Okay. Now we need to characterize all suboptimal Hankel norm approximations. So QA is one of them. Okay. QA is one of them. All right. Okay. So let's see. QA has dimension. QA should have dimension R in some sense, but it's also here. This is A transposed. Okay. All right. All suboptimal approximation can be made. For this purpose, we need to use linear fractional transformation. This is something peculiar to control engineering. Okay. And has a lot of interesting, this is an interconnection having a lot of interesting properties. Okay. Okay. This is how you build a linear fraction transformation. Okay. So you have the connection in figure 161. Then all the elements Mi, J, S, and Ns are all proper transfer function matrices compatible dimension in order that the loop is well defined. Okay, and to have the loop well defined, we need to satisfy this this relation. Okay, and then the closed loop transformation, okay, is G, which is of this form 1638. Okay, and it's usually denoted through this notation. Okay, through this notation. It also has a dual counterpart that can be written. Okay, we can have a look. This has also an implication if you look at systems from a network theory perspective. Okay, you can also have look at the things from an interconnection perspective. Okay, and now you have some interesting properties of the linear fractional transformation, okay, listed in theorem 162. There's a lot of properties if you have a look. Properties which we need, yeah, such as this one, okay, all right. And then you have a theorem, let the transfer function, okay. You need a sufficient condition for n to exist. So to extract your reduced order model in the Hankel norm sense, you get it from this linear fractional transformation. Okay. All right. And theorem 163 is telling you why or how. Okay. Okay. Is falling in region B from. Okay, matrix is a minimum state variable. Okay. All right. Now we are ready to characterize all suboptimal Hankel norm approximants. Okay. So we started with an original system GS, augmented it using adding 0 rows and columns to make it G augmented, and then found a square system QA with a realization A hat, B hat, C hat, such that the error, okay, between GA and QA is a scaled all-pass filtering, okay, emphasizing this gamma quantity, gamma being somewhere between the Hankel singular values R and R plus 1. So now if you want to compute all the approximants, it's rather, they say it's rather straightforward. Okay, whatever straightforward means in this case. So we consider now the set of all transfer function of dimension R stable, okay, real rational transfer function matrices, such that the A matrix of any associated minimal state variable realization R has all the R eigenvalues in the complex left half plane. Okay, so all the Q's, so we can parameterize all the Q's satisfying relation G minus Q infinity norm smaller than gamma. They are all given by the fractional transformation between QA we just built and any transfer function, okay, stable, such that this relation holds. So of infinity norm smaller than 1 over gamma. Okay. If you look, I'm talking now. Okay, we're all here, people from our faculty in control. You remember from the second year, the Euler parametrization, I suppose. Okay. You recall the Euler parametrization. It's similar, of course, in a completely different context. It's similar to the Euler parametrization, so we can parameterize all the suboptimal Hankel norm approximants. How? Using this linear fraction transformation. Okay. 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 So we can do a lot of manipulations. Okay. And look here, you observe 0 blocks in J yield G minus Q, okay, is lower fractional linear fractional transformation of G minus QA U, but G minus QA is EA, okay? And here you can compute the gamma inverse quite clearly, okay? This is not very easy, but it's been implemented in MATLAB, so you can check it out, the result in MATLAB. There is no need to perform this with a pen and paper, okay? And then you can get your reduced order models from this, okay? From this, okay? And you have all sorts of relations, very interesting, with respect to the gamma quantity lying in between sigma r and sigma r plus 1, because sigma r plus 1 is the key due to the basic relations with respect to the infinity norm, okay? All right. Obtaining some suboptimal Hank norm approximation of a square transfer matrix, okay? So we have parameterized all the reduced order models satisfying a Hankel norm error bound, okay? Now, how do you find the optimal Hankel norm approximation? Okay, how do you do that? And you pick, in this case, the gamma to be the R plus 1 truncated Hankel singular value of the original system. Okay. And apparently the previous construction is not possible in this case because you need to invert matrix A. Okay. And in the optimal case, E is usually singular. Okay. So for this case, we consider a square transfer matrix. So this is for the MIMO case. Now, a square, yes, a square transfer matrix G. Okay, and find the limited family of optimal approximation. Then you can also extend this to non-square transfer function, and you can expand and get the optimal Hankel norm for everything. Okay, and this is showing you how you do that. Okay, you pick the Gramians to be of this form. Okay, all right. So you bring the Gramians in this form, and then you partition G according to P and Q in A11, A12, and so on and so forth. Okay, and then you can get all sorts of interesting relations, and you get your approximant in this form. This is the reduced order model you're able to compute. Okay, this is the reduced order model you're able to compute. And then you define the error system. Okay, you embed everything into Q to define your error system. Okay, and then you get some interesting relations. And this is the Gramian in 1661. It's the controllability Gramian of the error system. Okay, and then there is all sorts of relations that you can check. Okay, and then there is 1663 that yields the desired result, that the norm, the infinity norm, there is an infinity norm of the approximation error, and that's given by the R+1 Hankel singular value. Okay, Hankel singular value. Okay, and furthermore, if you have if the reduced order model is stable, okay, then there is other relations in sigma R+1 that hold, okay, and then finally you achieve this very important result that you can completely and definitely compute the Hankel norm of the error as the R+1 Hankel singular values. Okay, and there are discussions about this error norm and about the implications of such an error norm. And you can also do this in the general case for non-square transfer functions. Okay. So what you essentially do, if your given transfer function matrix actually is not square, then you make it square. How? By augmenting it with 0 columns or rows or rows. Okay, and then of course you can start repeating. You can repeat the same procedure. You can repeat the same procedure, and you get the desired result. Okay. Okay, and there's also other interesting details, but you also get a class, the entire class, so you can parameterize the entire class of all optimal Hankel norm approximants of a non-square transfer function matrix. So you can get a very nice parametrization, okay, of this. This is very interesting, okay? All right. Then what happens for stable approximants, and so on and so forth. I'm going to leave you to read all these things by yourself. Then there is finally the connection with the balanced truncation approximant, having some very interesting relations between the error bound in balanced truncation and the error achieved doing optimal Hankel norm approximation. Okay. Okay. Then I also embedded here the same lesson, but discussed by the book of Antulas in chapter 8. Okay. And it's interesting, it shows you here a diagram of the all-pass construction, and it shows you actually it was not mentioned before that, but this result is called the Adamian-Arov-Krein theorem, or the AAK theorem, expressing this relation. This is in terms of Hankel matrices and Hankel operators. Okay. And based on this, then you build up the whole discussion I just showed you earlier. And then you get the construction of the approximants and all the discussion previously made. However, a bit more extensive than what we saw before. So you've got more explanations here and more interesting details. You can have a look. Okay. What I'm interested in at the moment, because there is not much more I can tell you, but you have to look it up yourselves, is I'm trying to go back to the MATLAB, if I can, and I think I can. And let's just check for a minute and see how it's done. Okay, how this is done for in MATLAB. Let's see how MATLAB deals with Hankel norm approximation. So we go to the basic command modred, and we look. So simplifies, nice word. The state space model sys by discarding the states, okay, the future, okay. So for balance truncation, it shows how it's done. Truncate is the method. I'm not sure whether this okay. Help. No. Okay, let's go to the let's see here. Hankel norm approximation, MATLAB. How you do this in MATLAB? This is interesting, huh? That's what I'm interested in for the time being. I haven't used this before too much. Hankel MR. Look, so there exists Hankel MR. G red over G struct array. Okay. Containing the error bond of the Hankel. Okay. So there exists. You see? Examples. Look. Stable system. Okay, so this is very interesting that the Hankel norm, I forgot to mention this. So the Hankel norm is it can be used also for unstable systems. However, it cannot be used for systems, and we mentioned that. It cannot be used for systems having eigenvalues on the imaginary axis. Okay. And here you also have a description. A description of the procedure, and furthermore, you've got some interesting references. Keith Glover, a famous control guy from Cambridge. You can look up also these references and read a little bit more about this. But the condition here is Hankel MR. This is interesting. Okay, let's just take this code. And let's do this for something very simple. Okay, So for instance, we have these guys with controllability, observability, and all these things. Let's see, this guy here, huh? Min sys, we have a min sys here. All right. So let's run this guy. All right. I'm not going to use this any longer. Let's put this code. We're saying G is min sys. I'm not sure if this is working. Oh, but it's working. It's actually working, you know. So you can play with, so this command is Henkel MR, okay? We have, so our minimal system, we try to reduce, okay? Please select the desired order. Let's make it 1. It's doing something. So these are the singular values if you do the approximation of order 1. It's very interesting. So these commands actually work, okay? So this is for a simple system. G is a simple 3x3 system. Okay, so this is a transfer matrix. This is the minimal realization of a transfer function of order 3. And this is the result when you apply the Hankel model reduction, okay? So this is the simple one. This is the one with 20. I don't know what 20 is here. I have to look at the... So let's put here help. Help. Hankel MR. Well, there is quite some help. So you have G order, keyword, I don't know what keyword, and value, performs an approximation for G such that the infinity norm is less than the sum twice n smaller Hankel singular value. So the infinity norm is less than, okay, so just like imbalance truncation. For unstable G, the algorithm is working by first splitting G into a sum of stable and unstable part, reduces the stable part, then add the unstable part back for the final output. The unstable part is kept as default. Okay. So essentially, the reduction is performed only on the stable part of G. Okay. Order is an integer array with desired orders of the reduced model. A batch, okay, can be specified for a pack of reduced order models. Aha. Keywords: max error or weights. Okay. So the maximum error can be a real number or a vector of maximum errors to get several reduced order models, okay? All right? So it's very interesting. It's very interesting. So and there is also reduce. What does reduce mean? Okay, so these are commands I haven't used before. Sorry, I'm sorry to tell you. This is new. Reduce. Reduce main interface to model approximation algorithms. Groups all Hankel singular value based model reduction routines. Wow. So you also have here, very interesting, all model reduction. You can also play with reduce. So Hankel MR is one of them. And you can also play with reduce when you get the assignments in lab 5 or 6 about model reduction. You can perform this playing with these functions, okay? All right. Please tell me or express your desire to show me any questions. Have you got any questions, please?
I have a question.
Yes, please.
In Obinata book,
In the book, yeah.
there are some main points of the section,
Okay.
and there it says that the singular values
Mhm.
are the square root of the
The Hankel singular values are the square root of yes.
the eigenvalues of the product
Yes, of the product PQ or WM. Yeah, that's true. It's true. Because you had the relation, I don't have the board any longer. You had the relation gamma star gamma is sigma squared V.
Mm-hmm.
You see? So sigma squared, so the squared Hankel singular values are the eigenvalues of the operator gamma star gamma, or equivalently of the matrix product Wn. Yeah, it's correct.
But square root, it said.
No, again, the Hankel singular values are the square root of. So the square root of the Hankel singular values are the eigenvalues of the product Wn.
Okay.
Mhm. This is how you look at it. Huh?
Mm-hmm.
All right. Anything else?
No, right now.
Fine. The call is still open, so please do not forget about the assignments. Lab 4 is open. You have 1 week to complete the homework of Lab 4, of assignment 4. It's about minimal realizations, so it shouldn't be very difficult. You have to do some research and make comments and remarks about the systems you have and where you have to compute a minimal realization. Okay? Please also do not forget to start assigning yourselves the papers for the exam. And what else? If you have any other questions or any other issues I can help you with, please feel free to talk to me, okay?
Okay, thank you.
Okay. Okay, that being said, I wish you happy Easter, please. Have a happy Easter, safe happy Easter. And we'll meet next week because there is no lecture missed with holidays by ourselves, right? So we get full version of the this is what how I usually like it. Fine. So please do lab 4. And if you have any questions or you are interested in the subject and you want to discuss more, please feel free to talk to me. Okay. All right.
All right. Thank you. Happy Easter.
Right. Thank you.
Okay. Same to you. I'll see you.
Happy Easter. Bye.
See you. Bye. Thanks. Paștele mătii.